everyone, welcome back to this video on differentiability. In this video we are going to continue practicing problems on differentiation. Let us look at the first question. I'm going to give you hint through all these questions and leave the details to you, because we have already learned how to check continuity and differentiability of functions in the previous two videos. So let's quickly look at this given function, which is defined as e to power minus 1 upon x square sine 1 by x, as x is non-zero, so this is well defined. And at x equal to 0, the function is separately defined to be 0, and you are expected to prove that it's differentiable at x equal to 0. Now if you look at the graph of the function, it's very easy to see that it passes smoothly through 0. I've sketched the graph of e to power minus 1 by x square sine 1 by x using Wolfram Mathematica here for you to see that the graph is passing smoothly through 0. There is no sharp point. So you indeed have differentiability looking at the graph, but let's prove that ab initio. For doing that, you will be considering limit extending to 0 of fx minus f0 upon x minus 0, and it boils down to limit extending to 0. Fx is e to power minus 1 by x square sine 1 by x, f0 is 0, and you have x minus 0 in the denominator. So effectively this answer is limit extending to 0, 1 by x e to power minus 1 by x square into sine 1 by x. It is easy to see that this limit is 0 because you can rewrite this limit as limit t tending to 0 of t e to power minus t square, or you can rewrite it as limit t tending to 0 t upon e to power t square. Sorry, not tending to 0, tending to infinity, because I have substituted 1 by x as t. So since x was tending to 0, so t is tending to infinity. So this is an infinity by infinity form, which on one application of L'Hopital rule gives you that the answer is 0. And 0 into anything bounded. Sine 1 by x is a bounded expression. This limit is 0. So 0 into bounded is 0. So this answer is 0. Hence limit extending to 0 of fx minus f0 upon x minus 0 exists, and it's equal to 0. So you do have differentiability of the function at 0, and differentiability implies continuity, so you do have continuity as well, which was very evident from the graph that I had shown you just now. It's continuously passing through 0, and there's smoothness also, so you have both the features, both smoothness and continuity are there at 0. So let's quickly look at the second question. Second question is a routine question. It's a branched function, and you're expected to check continuity and differentiability at 0 and pi by 2. So I'm leaving this for you to practice on your own, and if you have any doubt, you can please put your doubts in the comment section. We would love to answer them. Now look at number 3. Question number 3 says that you have to test this function for continuity as well as differentiability. For continuity, you will just consider the left and right hand limit, and you will find out that the limit is existing, and you do have continuity at 0, but you will not be having differentiability. So I'm leaving that exercise for you, because we have done a lot of practice of similar questions in the previous videos. Just there's a little line of caution from my side. When you do this question, please keep in mind that e to power 1 by x as x tends to 0, do not blindly write 1 by x tending to infinity. You will have to check the sign. If x is tending to 0 from the positive side, 1 by x will tend to infinity, whereas if x is tending to 0 from the negative side, 1 by x is going to tend to minus infinity. Keep that in mind while evaluating this, and you will find that the function is continuous but not differentiable at 0, and similarly this one is also continuous but not differentiable at x equal to 0. Let me add one more question to this set for you to practice. Show that this function fx, which is given by x tan inverse 1 by x for x not equal to 0 and 0 for x equal to 0, is continuous but not differentiable at x equal to 0. So please try these problems, these 5 problems on your own, and convince yourself that you have learned the idea of differentiability and continuity well. In case of any doubt, please put your doubts in the comment section. We would love to answer your doubts and resolve your queries. If you like the video, please press the like button and share forward. Thank you so much for watching.